Alright, welcome back. In this video, we want to take this big giant mess of resistors and replace it all with a single equivalent resistor. So we're going to be hunting through here for parts that are in series and parts that are in parallel. And so the expression for series resistors, the equivalent resistance is just equal to the sum of all of the resistors that are in series with each other. So if there's 2 in series, we have R1 plus R2. If there's 3, we have R1 plus R2 plus R3, etc. For resistors in parallel, the equivalent resistance is just equal to 1 over, and then it's 1 over R1 plus 1 over R2, and so on, for however many resistors we have in parallel. So when we look at a problem like this, we want to easily identify things that are that we can isolate as just being series or parallel. For example, if we look here, you can see that this branch, it comes off and it goes somewhere and it comes back to somewhere else. And so this is 2 resistors that are just in series with each other. Or if you look down here, we have 2 resistors that are parallel to each other, basically from this point to this point. Really, it's from this node to this node. And something that can help is if we shade on the nodes. So let's actually do that. Let's color this one in blue. We can just pick random colors for them. It doesn't really matter. And then we can fill out all the other nodes with different colors too. So let's just do this methodically one at a time. We can see that from the green node to the blue node, there's 2 resistors in series. So we can just find their equivalent resistance. It is just 0.5 ohms plus 0.5 ohms, and that's an equivalent resistance of 1 ohm. So what you can do if you have the space or you have an eraser and this is in pencil, you can just erase what you had before and replace it with a single equivalent resistor with the known amount of equivalent resistance. So in this case, it is 1 ohm. And then once we have this here, we should be able to recognize that from the green node to the blue node, we just have 2 resistors in parallel. So we can come over here and fill in the values. So for the equivalent resistance of these 2 resistors, we have 1 over 2 ohms plus 1 over 1 ohm. So this gives us 0.5 plus 1, so this is 1.5 in the denominator, and 1 divided by 1.5 is 0.667 ohms. And we can replace the 2 resistors with a single resistor of that amount. Okay, the next most obvious thing that we can do is probably looking at this one here. We just, from the yellow node to the blue node, we have 2 parallel resistors. So let's come here and update our values so we can get rid of this stuff. And we have 1 ohm and 2 ohms. Well, those are actually the same values, so we still have 1.5 on the bottom, and then 1 divided by 1.5 is 0.667. So we can erase these and replace them with 1 resistor that has 0.667 ohms of resistance. Okay, so the next thing that we can do then is looking at these 2. They are in parallel with each other, going from the yellow node to this pink node. So let's come down here and update this expression again. So we have 1 over, actually let's erase everything first. So we have 1 over 1 ohm plus 1 over 0.5 ohms. So this expression is 1, this is 2, so we have 3 on the bottom, and 1 divided by 3 is 0.333 ohms. So we can replace these 2 parallel resistors with 1 single resistor of 0.333 ohms. And then once we have that here, we can see that this resistor and this resistor are in series with each other, basically connecting the yellow to the blue node. So we can combine those in series. So we just have, let's update these numbers in here for this value. So we have 0.333 ohms plus 0.5, so that gives us 0.833 ohms for a single equivalent resistor here. And once we have that set, we can see that from the yellow node to the blue node, we just have 2 parallel resistors. So let's update this expression. So for the first resistor, we have 0.667 ohms, and then the other one we have 0.833, and that all simplifies to 0.370 ohms. So we can replace those 2 parallel resistors with a single resistor with that amount. And then now we've got 2 resistors in series going from the green node to the blue node. So let's update our series expression up here. So we have 2 ohms plus 0.370 ohms, so that's 2.37 ohms that we can replace these 2 series resistors with 1 single equivalent resistor. And now going from the green node To the blue node, we have two parallel resistors, so we're back to the other expression down here with the 0.667 ohms and 2.37 ohms, which simplifies to 0.521 ohms. So we can replace both resistors with a single equivalent resistor that connects the green node to the blue node. And then our last step here is seeing that we just have two series resistors left that we have to combine. So let's update these values up here. So we just have 1 ohm plus 0.521 ohms, so that's just 1.521 ohms. And then we can make the final adjustment here, so we have a single equivalent resistor with a resistance of 1.521 ohms. And that is the total equivalent resistance of this circuit. So we reduced it from this big mess of a bunch of resistors everywhere down to this. So from the perspective of the battery, it's going to put out the same amount of current for this single resistor as it would for this whole more complicated circuit.